Hey guys, this is Josh from Leet where we explain programming questions as simple and concisely as we can. Today we'll be talking about the problem max area of islands. According to some Google search and LeetCode, this problem is commonly asked in Google, Facebook, and Amazon. So not only will you get a good bang for your buck in terms of learning about graph problems, there's a good chance you might actually see this problem. We are given a non-empty 2D array grid, which contains zeros and ones. We want to find an island, which is a group of ones representing land, that's connected either horizontally or vertically. And then we may assume that all of the edges in the grid, which is outside of the matrix, is surrounded by water. The goal of this problem is to find the maximum area of an island in our given array. And of course, if there's no island, then the maximum area is 0. In example 1, the answer is 6 because we have 1, 2, 3, 4, 5, and 6 ones connected horizontally or vertically. Note that the answer is not 11 because these 5 over here is not horizontally or vertically connected to our 6 island. In example 2, we're just given a matrix of zeros. The max sum is 0 because there is no island. For those of you who are familiar, this problem is very similar to the number of islands problem, where we count the number of islands in a 2D matrix. However, the twist in this problem is that we want to find the largest island instead. We'll start off by traversing through our array until we find land. And then once we find land, we want to do a DFS traversal on everything that is touching our land, because that's the only way we can tell if our land is attached to another piece of land. So we'll explore all possibilities on our first strip of land, then we'll move to our second strip of land and explore all different directions, up, left, down, and right. And then the idea is that we'll just explore every single piece of land, add up the sums that we encountered, and then return it back to our starting value. And then that will give us the maximum value. There's one problem that we'll encounter, and that is how do we make sure that when we traverse through our matrix that we don't actually end up double counting. To do that, there are a number of ways. We could create another matrix, for example, and it could be a matrix of false, where we would set the value to be true whenever we've visited the matrix. And then if we ever visit a index which is true again, we don't explore it. However, the classic solution to this problem is instead of allocating another matrix to store this value, we can just modify the existing matrix itself to store the value. We can modify the existing index in the matrix to mark our seen value. How we would accomplish that is whenever we explore an island, we would just change the value from 1 to 0. In our DFS algorithm, when we see it again, we'll check to see if it's 0 or not, and if it's 0, we skip our navigation and then try a different path. We can essentially solve this problem in 6 steps. First, we'll navigate through our matrix until we hit 1. So we start in our top left corner. We just continue traversing our little ship until we hit land. And then once we hit land, we go to step 2, where we do a DFS traversal by passing in our current indices that we are at and our starting sum, which is 0. In our recursive function, when we do our depth first search, the first thing we want to do is we want to make sure that we are within bounds and we are on valid land. Starting off at the first location, we are indeed in bound and we are on land. Once we have ascertained that, we just need to set our current location to be seen, which basically means we set it to be 0. For those of you familiar with graph problems and DFS and BFS algorithms, this is essentially us having a visited set where we store our node. In this instance, our visited set is just the indice that we are on the grid itself. After we've marked our indice, we increment our sum by 1. So right now it's 1. And then we recursively explore all 4 directions of our current index. So that means we will explore the left side, the top side, the right side, and the bottom side. And then we just repeat our algorithm over and over until we hit our base case, which is when we are not within bounds or no longer on any land. I won't go through the full details of the implementation yet because we'll do that in the live coding section. However, the idea is that we'll keep a sum. We'll start with 1. And then when we go to the indice below it, we increment that to be 2. We explore the left, and that will give us 3. We return 3 back to our right indice, and then we'll explore, let's say, the bottom. And then with our new sum, which then we get 4, and then that will go 5, and then we'll pass them back up. Then we'll explore the right side. We'll get the sum 6. We'll pass that back. And then we'll try exploring the top one, but because we've seen it, we don't process it again. And then we'll pass 6 as the answer to our problem. Of course, the matrix might have more than one island, so we can't just stop exploring, and we'll just have to continue iterating through all of our matrices until we're sure we have explored every single island, repeating the same algorithm that we did on every single one that we encounter until we've explored everything in our matrix. And because we marked everything as seen, all of these ones that we have here are actually zeros, so we won't count them as valid land. The runtime of this algorithm is O of row times column, because we are exploring all the grids inside our matrix twice. The first time when we're just trying to navigate it to find land, and the second time potentially if it is a 1, and so we're exploring the land. The space-time complexity of this problem is O of 1 because we are using the matrix itself to store the indices that we visited. If we can't use the matrices itself to store this value and we make another 2D matrix, then our space would be the size of our grid. The first thing we want to do is we want to declare a max variable because we'll be exploring the grid that we're given for multiple islands. We want to keep track of the island that has the greatest area. So the first part of our algorithm is that we will explore every index in our matrix, and then whenever we hit land, we want to apply our depth first search algorithm to find all connected land masses to our starting value. So what we're doing here is we are exploring all of the indices in our matrix. If we hit land, we will calculate the area of our land and compare that with our max value and set whichever one is bigger to be our max value. And then we'll just continue exploring the rest of our matrix until we have visited every indices. So specifically, we start at I equals 0 and j equals 0. And then we just continue iterating through our matrix until we hit our first land at I equals 0, j equals 2. Now back in the code, we need to define our DFS algorithm to help us find the maximum area of this specific island. What we're about to implement in our helper function is actually a very common structure for doing DFS on matrices. First thing we want to do is we want to make sure we are within bounds. Specifically, if we don't accidentally end up outside of our j bounds, before our j bounds, outside of our I bounds, or potentially before our I bounds. In a way, you can also think of this as our base case. We know that we've hit the end when our index is out of bounds, or potentially if we hit a 0. So let's clean this up and get coding. As we described, if we are out of bound, which is our base case, when this happens, all we need to do is return the area that we're calculating, because remember, we are counting all of the area and passing it along to count the number of land masses on this specific island. So now that we addressed our base case, it's time to address our main recursive case, or just the main DFS algorithm. So in the meat of our recursive function, what we want to do is we want to set our current indice to be 0, which is us marking the location we're at, let's say over here, as visited, so that if we ever see this value again, we don't enter our base case and we don't try and explore it again. We increment our area, which will pass in our recursive function to help us calculate the total area of our island. And then we have our 4 recursive calls. We want to explore all 4 directions that is connected to our land mass. On the whiteboard, we want to look for every land mass that is above our current index, to the right of our current index, below our current index, and to the left of our current index. And then we will pass our current area that we have, and then it will recursively add and increment that value and then return it when we are finished recursing through all 4 directions. And the end result will be us having the maximum area of the land that we are on. Now, let's quickly walk through this. Like we mentioned earlier, we were at I equals 0 and j equals 2. Our current sum is 0. The first thing our algorithm does is we set our index to be seen. So we turn this to be 0. We increment our area to be 1. And then we traverse our 4 directions. First, we try going up. So when we're up here, we are at I equals -1. Oh, well, actually, sorry. This is incorrect. We actually go down first, and I minus 1 is up. Following our actual code, we do I plus 1. So we end up on I equals 1. So we go down. And because at this current location, we are not out of bounds and it's not 0, we don't return our area, we would do the exact same thing in our algorithm. We would explore our current land mass. We would set this to be 0. We increment the area that we're given to be by 1, so it's now 2. And then we follow the first step in our algorithm, which is we once again go down. We're back down here with on I equals 2, j equals 2. Mark this as seen. Set our sum to be 3. Explore down again. And now our sum is 4. Now we try going down again. We are out of bounds of our matrix, so we just return our area, 4, back up. So next, we try going to the right. Right is 0, which hits our base case, so we return our area back. So we're back here. Then we try going up again. And because we already marked this landmass as 0, we hit our base case, and we just return our area, so we go back down. And then we go left, which as we see is also 0. So we return 4 back to our starting location. And then finally, we return our area 4 back to the recursive function that called it, which is at over here at I equals 2, j equals 2. Now I won't bore you with the same logic, but now we would do the exact same thing. We would explore all 4 sides and see that it's 0. We return 4 back to here at I equals 1, j equals 2. We would now explore the right side. Since it's a 1, we haven't hit our base case. And then we follow our recursive case and set the value to be 0. Increment our sum, which at this point is now 4, to be 5. And then we explore the 4 sides again and realize that everything is a base case. And so we just return 5 back to the function that calls it, which then would continue trying all directions until it hit the left side. Set this to be 0. Increment our sum of 5 to be 6. And then we just continuously pass it back. And then eventually we'll have a sum of 6 in our starting indices. Now this is a mess, so I'm going to quickly clean up everything on our board. All right, so here we are again. Notice that all of our previous ones are now set to 0, and we have our max sum of 6. We store that 6 inside our max value, and then we'll continue iterating through our grid. Long story short, as you can see, since there is no ones left, we will continue traversing through the rest of our matrices and not hitting land. And then we'll return our max value, which is 6, which will give us the answer to this question. If there were other islands that we hit, we would just do the exact same algorithm, count our max, count our area, and see if it's greater than our current max value, and then just continue along. Now let us run this code and see how we did. And there we go. We have a solution. If you didn't know how to handle DFS on matrices before, this is something I would highly recommend, as I've personally hit these types of questions multiple times, and so knowing how to handle them will definitely pay off dividends. Now, if you found this video helpful, please consider hitting the like button and maybe even subscribing to get daily updates. Otherwise, I'll catch you in the next video and have a wonderful day.